So it seems that we are alive. We have 4 participants. Thank you very much of coming with us. I want to remind that we have a chat in the right side of the panel. I will invite people to just say hello in the chat. This is just to confirm that you are listening to us. Just say hello. I'm going to type in the chat. Okay, perfect. Thank you very much. So we're going to start this presentation right now. Give me a second. So welcome to this presentation, Addressing All Learners in the Math Class. This is a joint presentation between myself, Paulino Preciado from University of Calgary, and Ayman Al-Harra from University of Acadia.
Hello, my name is Ayman.
Go ahead.
Yeah. Hello, my name is Ayman Al-Jarrah. I am assistant professor at Acadia University. I would like to begin by acknowledging the Mi'kmaq, the ancestral and unceded territory of the Mi'kmaq people. I acknowledge the treaties of peace and friendship, and I thank the Mi'kmaq people for sharing their homeland with us. I arrived in Calgary in 2012 and have started my position at Acadia in 2019.
I'm Paulino. We like to take this opportunity to acknowledge the traditional territories of the people of the Treaty 7 region in southern Alberta. The city of Calgary is also home to Métis Nation of Alberta, Region 3. I acknowledge that First Nations were deceived into giving up their land and treaty promises are still not being honored. Paulino arrived to Calgary in 2011 and acknowledged that. This land acknowledgement is just the first step towards reconciliation, and we encourage you to understand the history of the land you reside in. Okay, after this short presentation, we are going to ask you to please, we wanted to create an interactive presentation. We couldn't find the tools to do that in the tool for the conference. So we're going to be forecasting as well from Zoom. If you want to stay in field loop, that will be fine. If you are able to go to Zoom, that would be we may be able to engage in conversations. Now there are a few people, and perhaps we can do it everything from a feed loop. But if you want to join us in Zoom, I'm gonna copy and paste the information. We are going to ask you to. So there's a link in the chat. You can just follow the link, and the passcode is math. We are planning to use the breakout room just to have a quick, being able to have a quick conversation with you. That's all what we want to do. We are doing this because we want to encourage some conversation among participants, and we want to hear from you. So I want to continue forecasting from here. We want to hear from you, so I invite you to, give me a second. We want to make this interactive. We want to hear from you. That's important for us. And for that reason, we can use Zoom, or we are going to just invite you to participate also in Jamboard. There's another link to this Jamboard. And the question is really quick. You can just select text and share with everybody your answer. What are your main challenges in teaching mathematics? And I hope you have let's take 3 minutes we want to hear from you. What are your main challenges? And we hope we address those challenges in today's session. And we stress that we believe in interaction. So we would like to see your comments. You are also welcome to show your comments in the discussion topic. Sorry, in the panel aside the presentation.
Paulino, do you see anyone on Jamboard?
No, but I need to step back and forth. I get a comment. I see someone commented in the chat. Say hello, Chris and Tony. You're also welcome to type in the chat. That would be perhaps easier.
You can respond to the question in the chat.
Yes, because there are few people, maybe the chat is enough. We were planning for more people here, but with few people in the room, the chat may be enough. Okay, thank you. We received feedback from the administrator that appears to be the forecast appears to be stopped. It seems to be streaming according to what I see. I will continue with the presentation anywhere. Because we have few people, we may not use Zoom. I'm gonna stop the Zoom session to avoid any problem with the two platforms. So I will go back to my presentation and I will please, because I don't see what's going on, I will ask you to let me know if you can see my screen now in the chat, please. Oh, I'm fine. I received the feedback from the administration. I need to jump between window to window just to make sure things are working well.
I think I can see your screen now.
Okay, thank you.
Yeah. So
I will continue. We just wanted to bring your attention to a few things we think are important. We'll talk about the madmans project we started in 2013. This is a project that focused at elementary level. With 3 school districts in Alberta, there was intensive research in the classroom and professional learning for teachers. We have actually results from the performance in the Canadian test for basic skills that show a consistent growth in students' performance. This is following the same students from one year to the next, and we have evidence that this approach actually has made a difference. The rapid model is based, which is what has developed from this research. I will explain what is the rapid, but it's based on the one hand, on the nature of mathematics. It focuses a lot of the mathematics. On the other hand, it focuses on cognitive sciences. It focuses on the principles that the brain is plastic, working memory is limited, minds are attuned to change, that's where we use variation, and minds link overlapping events. So what is rapid model? Rapid stands from raveling, prompting, interpreting, and deciding. And raveling has to do with how mathematical ideas are interwoven together and how we actually present to students these ideas so students can make sense by raveling the mathematics by themselves. Prompting refers to what we present to students. Interpreting is the constant process of the teacher looking at what the students do in order to make a decision. That's deciding, the last part of the rapid model. So the rapid model divides into the raveling, which is the mathematical part, and the prompting, interpreting, and deciding, which are supposed to be continuous cycles around a session in where the teacher prompts to something, interprets, and then decide to continue with the lesson or to adapt. Sometimes the adapt is if the teacher notices that the students are getting trouble, stop right there and address some trouble, or sometimes students are doing well and the teacher may decide to present further challenges to students. But the point is to do this like almost minute by minute, especially at the beginning of the lesson. What we have presented, this presentation is a very, very quick overview of the model. There's no time to go into the whole thing, but in madmans, we have developed the madmans online course. It is a free course for teachers. You can access through www.structuringinquiry.com, and you can create an account and take the course. For today, I'm going to present just a quick overview of some of the ideas of the course. So I will start with something you may have here about the math wars, which is you may be familiar with this, the traditional versus progressive approaches, in which traditional focuses on direct teaching, memorization, computation, basic facts, whereas the progressive approach focuses on problem solving, inquiry, personal strategies, and conceptual understanding. And some people take some extremes. Other people argue that there should be some balance, something in between. What we argue is that we need to take a different approach. This is not black and white, where this is more like a colorful thing. We need to see this different. And I hope that that presentation will help to take this, to see these things in a different way. I will talk a little bit about arithmetic operations, where arithmetic operations is not just something, a tool for computation. It's not only also, that will be the traditional perspective. It's not only also a place for students to create their own methods, for example, from the traditional perspective, but it's a great place to dig into the properties of arithmetics, something that will help students later on with the flexible thinking and even creativity, and of course, problem solving. So I will talk about algorithms of multiplication and division. At this point, I'm gonna stop sharing pretty quick. I just want to check that people can observe what I am presenting. So please let me know in the chat if you were following the presentation. Just tell me it's fine. Continue. I just want to make sure that people are following before I continue with the presentation. Or perhaps, Ayman, were you seeing the presentation?
Yes, yes.
Okay, thank you very much. I will go back to the presentation. It's just because in my experience, sometimes we just keep talking and we didn't know that something happened in the other end. So I will continue now with presenting these algorithms. I want to remind that this is not about just calculation. This is a lot about raveling mathematical concepts. And I'm picking up algorithms because it's something that is often related to just learn a procedure. But I think with this alternative, we can see that students will get a procedure, will develop a strong conceptual understanding that will allow them for flexible thinking and even creativity. So I want to we focus on something we call critical features, things that people have to notice. So in this case, let's think of multiplication as repeated addition as an array. We can see right away, for example, that it's easy to see that commutativity applies here. If I want to make the multiplication, I can separate the sum of 16 as 10 plus 6, and actually I can distribute the multiplication. This is a distributive property of multiplication. This is essential for mathematics at all grade levels. And usually the algorithm for multiplication actually does this. But in fact, we can decide to split in different ways. We can split in many different ways as we want to. And that's even this one. So let's say instead of multiplying by 10 and then 6, let's multiply by 20 and then subtract 4. So I can find 4 times 16 by multiplying 4 times 20, 80, and subtracting 4 times 4, 16. So 80 minus 16 is 64. So that's what I mean, that when we focus on this, actually that may give room for creativity. But in fact, okay, I will stop here. If we have enough time, I will ask people to engage in these operations. What I want to stress at this moment is in the left, that will be that what we will ask students to engage and try to apply these ideas, however they want, to address those questions. And in the right is if someone is already done, and this is very important, if we have people who have done that part in the left, they can continue with further challenges. This is something that often we call the bonus. So people who need more time, they will have the time to focus on the left, which is kind of the core activities. Those who are done, and they can extend their further learning, we are addressing their needs because they extend their learning to more challenging questions about the very same idea. So this is something important, and this is one of the strategies we have noticed in madmans. Always prepare something for those who usually finish earlier, so they can further their understanding of mathematics, extend in the same idea, but with further challenges. Okay, I will go back to the idea of what are these critical features for the algorithms. And something often called unitizing is think the numbers in terms of units. This is similar to working with blocks. So 5,031 means 5 blocks of or cubes of 1,000, 0 blocks of 100, 3 blocks of tens, and 1 unit. This is a very powerful idea when we look at the algorithms. I want to present this idea for the how distributivity applied in the algorithm for division, the long algorithm for division. So basically, the first step is distributivity. If I going to divide by 2, I separate the number in a sum of other numbers, and I can divide one by one and then add them all together. This is the first part that we often don't stop to explain to students to do, and the algorithm actually does that. The second part is what I call the unitizing. So let's unitize. Let's think in terms of units: 8,000, 300, 5 tens, and 4 units. And you will notice in the right that each column corresponds to 1,000, hundreds, tens, and units. So that's why the order matters. And when we explain the algorithm, we actually can prompt attention to students to the columns and the meaning of each column, and that's why we have to place the numbers in the corresponding column. Now, the next step will be, well, this is when we say 8 divided by 2, actually what we mean in the first step is we're going to divide 8,000 into 2 groups of equal size. So this is not 8, this is 8,000 divided by 2, but 1,000 as units. So the answer is 2 groups, 4,000 in each group. That's the 4 of the first answer. We have performed the first division. And then we move to once we have done with the 1,000, we move to the hundreds. So when we look at the hundreds, we do the same. We have 3 hundreds, and we want to divide 3 hundreds into 2 equal groups. In this case, it will be 100 in each group, and we have a remainder. That's what the algorithm does. So we have performed as far as we can with hundreds. Then for the next part, we have to focus on the tens. Here, I want to make a huge distinction. The difference between telling we drop the 5 to we put together 105 tens to make 15 tens. So that's not 50, that's 15 tens. Now we can proceed here with the division. 15 tens divided into 2 equal groups. It's 7 tens in each group. We have a remainder of 1 10. And then we apply the same procedure. The 110 will become 10 units. We put them together with the units, and then we can proceed with the last part of the division. And then that's we go back to the number, and then we can write the answer. So the algorithm does all that, but it's behind the scenes. What I want to stress here is we can still explain the algorithm, the same algorithm, in a way that actually I hope it makes sense why it works and why we have to keep track of the columns. The point is that we unitize and we are applying distributivity to divide each part of the sum. Again, one of my pain points is doesn't need to take too much time to get sense. This is just when we present the algorithm, we can stress all what is going on. Now, this was a very long example. If I were to teach the algorithm, I will start with a very simple example. But my purpose here was just to show what's going on in the division algorithm mathematically. So we can have this relational understanding on the algorithm of division with attention to big mathematical ideas such as unitizing and distributivity. If students understand that, that's my point. They may decide that a shortcut to this is just write the number as 8,354. And then, because we're divided by 2, we can take a shortcut right away. 8,000 divided by 2 is 4,000. 300 divided by 2 is 150. And 54 divided by 2 is 27. Just add them together and we got the answer. So actually, that's what I mean about flexibility. If people understand what's going on, they may see that they are shortcuts or things that they can do easily. That's if we think in just computation. But if we think also in the structure of mathematics, this is setting the ground to understand algebra, because those properties are the same properties for algebra. Once students get to algebra, if they think this way, algebra will be just an extension of something they have done already previously, if they understand the properties of arithmetics and these big ideas. Yeah, so this is actually much more short than the standard algorithm. Actually, I would say also easy. Now, when we are going to multiply, one of the critical features is to understand what happens when we want to multiply by powers of 10, by a number, by a power of 10, such as 5 times 10, 100, or 1,000. And what happens when we multiply the two numbers which are powers of 10. What I want to stress here, there's another thing important that I am using here, which is variation. I'm varying in each column, so one thing at a time, so people can start looking at the effect of this variation. In the second column, I do the same just with the 5. In the third column is when I start doing some other variations. First, from 50 times 1 to 50 times 10, then from 50 times 10 to 50 times 30, then from 50 times 30 to 500 times 30. And the students can actually pay attention to the effect of that. This strategy of systematic variation is very powerful to focus people's attention on critical features. I just want to remind that this idea of unitizing and grouping and ungrouping is also key. We can split into different groups and we can think of unitizing. For example, times 5 tens times 3 tens, which will be 50 times 30, equals 1,500, but it's the same as 1,500s. Now, let's put these ideas together for the algorithm of multiplication. And again, I want to show a way in which we can explain the algorithm in a way that stresses the properties of arithmetics. So this is not just for computation. And those properties, again, they could allow room for creativity and flexible thinking in the future. So the array I presented at the beginning, if we split 16 into 10 plus 6, and then we do the multiplications, that's exactly what we do when we work in the standard algorithm. This is very similar to what I show for division. We have the units columns and the tens columns. And they were multiplying 4 times 6 units and 4 times 110. I want to stress that the need to work on the columns. And one of the reason for that is because we are adding in this, adding by units. In this case, the units mean units, tens, hundreds, and so on. So you may be able to see that actually we're doing exactly the same than using the array model. And this is based on the distributive property. There's another common algorithm that many people suggest. This is called the lattice multiplication algorithm, which actually does exactly the same thing. So we split 16 into 110, 6 units, and then we have 4 units. In this case, the diagonals will correspond to the place value, hundreds, tens, and units. So 6 times 4 will be 24, but 24 is 2 tens and 4 units. So we locate the numbers in the corresponding place value. 4 units times 110, which is 40, that means 4 tens. So 4 goes into the diagonal of the tens, and then we add up together. This is exactly the same procedure and the same idea as the standard algorithm, and is based, again, exactly in the idea of this distributive property. I start with very easy numbers, but if I will apply, first I will show that this is, I already say that this is exactly the same idea as the standard algorithms. We split into tens and units. We pay attention to the position of units to tens, and we just add together. It's exactly the same. Once we notice this, I will say it's the same algorithm. It's just a different visual representation of the algorithm. Now I'm gonna contrast, look at, there's a variation here. I start with 16 times 4. Now I'm gonna do 76 times 4. Notice that the only thing that I change is the tens. This is an example of variation. So let's change one thing and see what is the effect of that change. So 6 units times 4 units is the same, 2 tens, 4 units. But now 4 units times 7 tens, which is 28 tens. The 20 tens becomes 200s, and the 8 tens is just 8 tens in the right position, and then we add together. There's something new here, though, that 2 tens plus 8 tens becomes 100. Something we have to consider. There was something else new here happening. So the first thing was the strategy is change the 7, change from 110 to 7. But there's something new here too, which now, in addition to having hundreds in the sum, when we group tens, we have 10 tens, and then we can actually think of these 10 tens as one more 100. Perhaps that was too much variation here because 2 things happen at the same time, and that may be difficult regarding working memory. There are 2 new things to pay attention here. There maybe it would be more reasonable to start with a lower number instead of 7 tens. That will be one example of what we do when we pay attention to the limits of the working memory. Well, look at the patterns of variation. So you start with 16 times 4, 76 times 4, and what about 76 times 24? So I'm going through this variation slowly to introduce every step a new idea. So now I introduce the 20 in 24. So we operate in the same way. We add together. And in this case, I just stop to show that we have 12 tens. And then 12 tens means 100 and 2 tens. And I need to consider that for the final operation. So that's kind of the new, there's 2 things new, perhaps new here, or at least one thing new, which is now two tens in 24. Then we have the regrouping of 12 tens, but that's something the students already did before. Now, I want to stress again that this lattice multiplication is exactly the same idea as the area model of mathematics, when we split into multiples of 10. It's exactly the very same idea. We are applying commutativity. So they are kind of big ideas behind this. I don't think it's necessary for students to master many algorithms for multiplication, but I think it's important for them to know that they are big ideas, and those big ideas are exactly the same for each algorithm. And those big ideas are actually will be the same big ideas when they move into algebra and other subjects. So I'm almost done here with this part. What I want just to stress is there's some people have mentioned that, yeah, conceptual understanding it's important, but it's very time consuming. I will argue that it's very time consuming if you look at the short-term goal. If you focus on conceptual understanding as a long-term goal, I will say that actually it's easier. And this is in the case of the algorithms, I will explain, I will give an argument. If students focus only on the procedures without too much understanding, just get the damn algorithm so you can add, subtract, multiply, or divide. Every operation involves a new set of rules. So every operation is totally disconnected. So maybe if we focus only one operation, this focus on conceptual seems to be more, but the big ideas for all the algorithms are actually the same. So that's what I say, this is a long-term investment. That once we notice that those big ideas apply to, are the same ideas that apply to every algorithm, actually, I hope that you see that there's maybe actually less to teach as opposed to just focus on procedure. That's what I mean, that we have to think on this long-term investment. And by the way, again, these big ideas do not only apply to algorithms, but also apply to further understanding of mathematics. That's all what I'm going to present here. The next part is going to be led by my colleague, Ayman Al-Harab. He's an expert in creativity mathematics. He's going to share with us his ideas. I'm in control of the screen at this moment, so I will suggest Ayman to just let me know when you want me to move the screen.
Yes, thank you, Paulino. Hello again. Let's start with the question: what is creativity in general? What is the creativity? If you have any response, or if you want to respond, use the chat, please. What is the creativity? Paulino, can you respond if you hear me? Like,
yes,
to the question? Yeah.
I changed the screen. Is that okay?
Yeah, it's okay. So I'm not sure. Any responses in the chat? So I will try to provide some definitions or descriptions now. The word creativity, both in its origins and in most of its different uses, reflects a kind of newness. It indicates bringing something new and fruitful into being. Previous research indicated that all broadly accepted definitions of creativity require two criteria: newness and effectiveness. For example, creativity was described as, or defined as, it doesn't matter, as imaginative activity fashioned so as to produce outcomes that are both original and of value. There are many accounts that offer fruitful definitions or descriptions of creativity. However, such accounts seem to be incomplete, given that they mostly restrict themselves to one vision of creativity, which is divergent thinking. In the field of mathematics education, doing and understanding mathematics are often described as creative processes. For example, a researcher described doing mathematics as creating mathematics that is new and significant to at least the doers. Can you move to the next one? Yes. So what's mathematical creativity? We define collective mathematical creativity as, or collective creative acts, as particular kinds of coactions and interactions of a group of curious learners while they are collaborating on an engaging problematic situation. Such acts, which may include summing forces, expanding possibilities, divergent thinking, and assembling things in new ways, trigger the new and the crucial to emerge and evolve. So as you see, this definition of creativity is based on 4 metaphors of creativity, which are summing forces, expanding possibilities, divergent thinking, and assembling things in new ways. For us, summing forces encompass the ways in which learners coordinate their efforts to enable productive steering towards a mathematical understanding. Expanding might be understood as broadening the learner's horizon by gaining new insights based on previous insights. Paulino, can you move to the next slide, please? Yeah. Divergent thinking requires students to consider many potential pathways, look in many directions, go beyond the problem's clearly given conditions and information, and think outside the box. Assembling things in new ways implies looking for associations and making connections. And by the way, making connections is one of the 5 mathematical processes of the NCTM's principles and in the NCTM's principles and standards document. We agree with the claim that creativity must first be permitted. It's latent in every child. So in the classroom, we need to address the creativity of all students. While teachers are expected to infuse problem-solving approaches into their practices to encourage students' creative thinking, the literature provides few tools to enable teachers to adapt rich mathematical tasks that have the potential to promote students' acts of mathematical creativity. So Paulino talked about variation and the critical features. We believe that the dimensions of variation of the object of learning have the potential to promote or to prompt and promote students' mathematical creativity. In addition, we, as teachers, we need to be aware of the critical features of the object of learning so that we can prompt learners' attention to them. I'm not sure if we can you move to the next slide, Paulino?
Yes, it takes a few seconds.
Yeah. The next slide, please. Yes. Do you see the screen? There is the chocolate bar problem on the screen now. Can you try it, please? This problem is rich with dimensions of variation to allow for the possibility of multiple potential solution pathways to emerge. So try it, please, and then I will talk about it. Or I will talk about the students or sixth grade students' work on this problem. Any comments about the problem? So I would like to talk a little bit about how the students or the sixth grade students who were assigned this problem approached it. I was hoping to share some videos, but I'm not sure, it's impossible to do that through feed loop. So I will just talk about their work. At the very beginning, the three students started by exploring the problem and initiating some potential solutions or some pathways for solutions. They started with the 1/4 option for John, and of course, 2/4 for Alex. And then they moved to the 1/10 option. They also discovered that they need to focus on John's and Zach's portions only. After that, they started to explore the dimensions of variation in the problem. So they ended up varying John's possible portions, which according to, they named them or they labeled these portions as their realistic options. Those realistic options are the 10th, 1/10, 1/9, 2/9, 1/8, 1/6, 1/7, 1/5, and 1/4. They also discovered that they could play with Zach's portions to get more possible solutions. In this case, they were trying to vary more than one thing at the time. According to them, since Zach's portion could be anything, they could take one of his parts, divide it into 4 equal sized sections, and give 1 to John and 2 to Alex. Then they could divide that last section into 4, give 1 to John and 2 to Alex, and so on. They could keep zooming in to the last section and do the same thing an infinite number of times. So now, at this time, they started, or they started to try to prove that the dividing process go on forever. Because according to them, this idea can be applied to all realistic options on the 10th, the 9th, the 8th, the 7th, the 6th, and the 5th. So at that time, I decided to intervene by focusing on a critical feature of numbers, which is density of numbers on the number line. So I asked them the question, do you know the number line? So all their actions and coactions after my question, or after they knew that they could use the number line, was focused on this critical feature, the density of numbers on the number line. What I'm trying to say here is that paying attention to the dimensions of variation and the critical features of the object of learning enable these students to creatively encounter the notion that there are infinitely many rationals between any two real numbers. So I think we should stop presenting now, Paulino, and ask for questions. Hello?
Yep. Okay, thank you, everyone. So we presented two things. And I hope you get this, that we present the madmans approach to teaching mathematics that is different than traditional and progressive approaches. We also mentioned that this could be used in different ways and could be applied even for creating flexible thinking and creativity.